From Chemistry Occurs, and we're here to meet our first contestant, Nick, about some of those supernatural events that have been going on in his life. Hi, this is Gibbs from Chemistry Occurs.
Hi, kids. I'm so glad you're here. I feel like I'm the first one who's actually got a curse in my house.
Chemistry is everywhere. Often in the past, people were convinced that someone was doing magic or had powers. It's my job to take each of these events that people are experiencing and show that it can be explained by chemistry. Nick, I understand you've been experiencing some really strange events lately. We were surprised by how extreme some of your stories were.
Yes, Gibbs, sometimes I can't even sleep at night.
Don't worry, Nick. I've never met any story that I can't explain with simple chemistry. So let's start from the beginning.
So it all started about 3 weeks ago when I was trying to go to the gym. My grandma needed me to make a solution of baking soda and water for her baking. She never writes down her recipes, so she told me to use my heart to know how much baking soda to add. I was really feeling this baking thing, so I added a good amount to the water, but I noticed pretty early on that something was off. I kept my cool. I just couldn't get the darn thing to dissolve no matter how hard I tried. So I tried to heat it up a little to see how that would help. It actually worked, but obviously it was too hot for me to carry. So I cooled it down in the freezer. And when I took the glass out, I was terrified at what I saw. Don't open your fridge, Grandma. That thing's cursed. It wasn't love that made my grandma's cookies so good. It was evil. Pure evil trapped in a box of baking soda. Okay, so Gibbs, are you ready to believe I have something supernatural going on?
Okay, so I have some news for you. Unfortunately, I don't think that your refrigerator is housing some ancient evil spirit in your baking soda. I think I can explain everything with some chemical equilibrium.
Okay, convince me.
Okay, first I want to give you some background to understand equilibrium. So dynamic equilibrium is where the forward and backward reactions are happening at the same rate. Therefore, the concentrations of your reactants and products stay the same.
Okay, so we have dynamic equilibrium when our forward and backward reactions are equal?
Not exactly. Your reactants and products don't have to be equal to one another, only the rates of the forward and backward reactions are equal. To calculate the equilibrium concentrations, you can use the equilibrium constant, or K. The equilibrium constant can be defined as the products over the reactants, where the letter in the bracket stands for the concentration of A. Now keep in mind that concentrations of solutes are in moles per liter, or molarity. Gases are in bar, and pure solids and liquids are omitted, as they always have fixed composition and are thus not changing.
What are they soluting?
Solutes are materials that can be dissolved by another substance. The substance that dissolves the solute is the solvent. Think about sugar and water. Sugar would be the solute, and water would be the dissolving solvent.
Okay, so in the case of my cursed baking soda, the solute is my baking soda, and the solvent was the water that I used. So, if I know the chemical reactions, I can plug that into the equation to know my equilibrium constant.
Perfect, but let's not get ahead of ourselves. To understand equilibrium, we also have to understand thermodynamics.
Thermodi what? This sounds a little complicated to me.
It may sound complicated, but it can be understood very easily. We can understand thermodynamics in terms of Gibbs free energy, which is followed as follows the formula seen here.
Hey, Gibbs free energy, just like your name. Did you discover this idea?
I wish. I wouldn't need this TV show if I had. Let's look at each part of the equation. Delta H is the enthalpy change or change in heat. When you run a reaction, you can have heat either come from the reaction or go into the reaction. These are called exothermic and endothermic reactions. An exothermic reaction will release heat and therefore cause a negative del H. And the opposite is true for endothermic reactions.
Okay, so if a reaction gets hot while it's running, then that means it's an exothermic reaction, and therefore would have a negative delta H.
Exactly. Now, the delta S is the entropy of the reaction or the change in disorder of the reaction. Reactions want to go to a more disordered state, and therefore, if a forward reaction has a positive delta S, it will reduce delta G. If a forward reaction has a negative delta S, that means the reaction would lead to a greater order and increase the delta G. The forward reaction will be favored if delta G is negative, either by a negative delta H or by a positive enough delta S.
Hey, my room is always disordered, so now I can explain to my mom. It's just the favorable state of the universe. So we know a negative Gibbs free energy of reaction will make the reaction favorable.
Again, it's not mine, but you're correct. Now, going back to our equilibrium constant, let's look at how it relates to the delta G. This is the equation where R is the gas constant. And if you have a negative delta G, you end up with a larger K, which means that your reaction is happening readily.
Okay, so if I have a larger negative delta G, then my reaction will happen faster.
No, remember that thermodynamics doesn't tell you about how quickly the reaction occurs. That's kinetics. Thermodynamics tells you how favorable the reaction is. Now let's look at the reaction that's occurring for your baking soda. You would see your baking soda break down in water like this, following this equation.
Okay, so the K, or equilibrium constant, then would be uh, K equals the products, right? Because you've already said that pure solids can't go into the equilibrium. Let's redo that. I'm sorry. Okay, so the K, or equilibrium constant, would then be K equals the concentration of the products times each other. Because you've already said that pure solids don't go into the equilibrium constant.
Very good. Now what you wrote is the solubility product, or the KSP. KSP is the equilibrium constant for when a solid salt dissolves to create ions in the solution. When the solution reaches equilibrium, then it is saturated. And if you add any more solid, it will not dissolve. Once you've reached this state of saturation, no more solid will be dissolved into the solution.
Okay, so there's a limit to how much solid I can dissolve, which would be the concentrations that equal the KSP. The amount of salt dissolved in the solution and the solid that didn't dissolve would be in the dynamic equilibrium like you mentioned earlier, because the forward and backward reactions are happening at the same rate, and therefore the amount of dissolved and solid salt will stay the same.
Excellent observations. Now let's actually take out some of that cursed baking soda and really try to understand this reaction. So, what happened when you added your big spoonful of baking soda? You reached the KSP really quickly. So, no more baking soda was able to dissolve in the water.
So since we've reached our solubility limit, none of my crazy stirring would have helped, right?
Exactly, so no amount of stirring would have helped you get more in. So let's move to the next step. So you heated your water. So let's see what happens when you heat it.
See? It happened again. How did all of our baking soda dissolve after we already reached the solubility limit?
Well, actually, what happened is when we calculate our KSP, it's for a specific temperature. When you increase that temperature, you disturb the system, and therefore your equilibrium set point shifted. This can be understood through something called Le Chatelier's principle.
I think I knew a Le Catelier's back in high school.
Not Catier's Le Chatelier. The Le Chatelier principle says that when the equilibrium is perturbed by changing the condition, in this case heating it up, the equilibrium will shift in the direction that will offset the change in that condition.
To offset the change in temperature, I suppose the dissolution reaction will absorb heat. In other words, it is endothermic.
Exactly. Another way to explain it is to look at the thermodynamic equations we saw earlier. If we substitute the second equation into the first, we'll get this third equation. So if our reaction is exothermic or releases heat and has a negative delta H, and if we raise our temperature, and then our K will decrease. If our reaction is endothermic or absorbs heat and we raise the temperature, then our K becomes larger. Think about it like this. Endothermically, the reactant plus the heat equals the product. If we raise the temperature, then the heat pushes the reaction and it will proceed to the right. If I open the freezer, I can cool down the glass of cursed baking soda and water.
Oh, so if it's an endothermic reaction and I cool it down, the KSP will get smaller, right? So that's why when I took the hot glass of baking soda and put it in the refrigerator to cool it down, it came out with clumps in it. It's because the baking soda had reached its saturation point, right?
Yes, see, it's easy when you understand the science behind it.
So in the future, all I would want to do is I would just want to put just enough baking soda to make it dissolve and then add my salt and my sugar.
I have some bad news for you. That won't work. I think you're still going to end up with some clumpy cookies.
But why wouldn't that work? I only put enough in to reach the saturation point.
So, we know that changing the temperature will shift the equilibrium, but what about changing the amount of material you have? So when you have chemical species in a solution that are not in equilibrium, you can use the reaction quotient, or Q, to see how the reaction will proceed towards equilibrium. The formula for Q is the same as K, except the concentration of the chemicals are not necessarily those concentrations at equilibrium.
Okay, that makes sense. If I just start a reaction, it won't automatically be in equilibrium. But how is Q related to K?
Excellent question. When Q is smaller than K, that means we have more reactants than in K, remembering that K and Q equals products over reactants. That means our reaction will shift towards the products to be in equilibrium. If Q is larger than K, then we have more products than in K, and we will shift towards the reactants to reach equilibrium. An easier way to remember this is if Q is smaller than K, then to get to Q, you have to shift towards the right. If Q is larger than K, then you have to shift to the left.
Okay, so how does this relate to me adding salt to my baking soda water?
So remember, your reaction products are sodium and carbonate, so when you add salt, which ionizes into more sodium and chloride, you've increased the sodium concentration.
Oh, I see. So now my solution isn't at equilibrium. And if I add more sodium, my Q will become larger because my products increase. My reactions shift towards the reactants, so more baking soda precipitates in the solution.
Perfect. Keep in mind salt also has a KSP, but it's bigger than baking sodas. So when you add more sodium to the solution, the baking soda precipitates out. But if we add a ton of salt, we'll eventually add enough salt so that they'll both precipitate out.
I never knew science could be both fascinating and scary as a paranormal curse.
See, there's nothing scary happening at all, and luckily you aren't cursed.
Yeah, I guess I'm not cursed after all.
You sound kind of disappointed.
No, I'm not disappointed. It's just, I've been at my grandma's house for over a week now, and I haven't had a single cookie because I thought her baking soda was cursed.
Alright everyone, this is Gibbs from Chemistry or Cursed, and we are deeming this a +1 for chemistry. Good night!
Did you?
Hear that noise coming from over there? Yeah, should we...
Maybe we should check it out for science.
Okay, well, with that, good night everybody!